Somewhere under miles of ice, an ocean is moving in the dark. Europa may have one. Enceladus almost certainly feeds one into space as mist. Titan may be hiding one beneath its thick shell. You are here to follow the evidence, how we learned that cold, distant moons can still keep liquid water, sealed away from sunlight. The cabin around you is quiet on purpose, with only a low mechanical hum and a few steady lights. It's the right setting for this kind of journey, because the clues you're following are subtle, faint fractures in ice, slight tugs in gravity, and magnetic signals that only instruments can hear. A subsurface ocean is exactly what it sounds like, liquid water trapped beneath an outer crust of ice and rock. No visible waves. No open horizon. Just a hidden layer that can persist for ages, warmed gently from within and protected by its own frozen roof. That roof is what makes these worlds so compelling. On Earth, oceans sit in the open air, constantly exchanging heat with the sky. Out there, the ocean is buried, insulated, and quiet. The surface can look still while the interior remains active, like a river running under winter ice. So the question comes quickly and stays with you: how can water remain liquid so far from the sun? In the outer solar system, sunlight is weak, and the cold is relentless. If you only judged by temperature at the surface, you would expect endless frost and nothing more. The first answer is simple physics. When water freezes, the ice floats, forming a lid. That lid slows the escape of heat, the way a blanket slows the loss of warmth from your skin. An icy crust does not create heat by itself, but it can keep small amounts of heat from vanishing too quickly. The second answer is chemistry and pressure, working quietly together. Salts mixed into water can lower its freezing point. Under a thick shell, pressure rises, and the behavior of ice changes with depth. Instead of one clean boundary between solid and liquid, you can get layers, rigid above, softer below, where liquid can persist. Then there is the deeper source, heat from the inside. Some of it comes from radioactive elements slowly releasing energy within rock. But the most dramatic warming, on some moons, comes from gravity, steady, repeated flexing that turns orbital motion into heat. You can picture tidal heating without forcing it. A giant planet pulls on a moon as it moves along its orbit. If that orbit is not perfectly circular, the pull strengthens and weakens in a repeating cycle. The moon flexes, and internal friction does the rest, warming the interior the way repeated bending can warm a piece of metal. Long before any spacecraft measured these effects, the story opened with a telescope. In the year 1610, Galileo Galilei watched Jupiter and noticed 4 bright companions changing position night after night. Io, Europa, Ganymede, and Callisto became proof that worlds could circle worlds. For centuries, those moons were only distant points of light, easy to imagine as frozen and finished. From far away, stillness looks like permanence. But as your journey begins, you carry the central surprise close to the surface of your mind. In the coldest places, oceans can hide, and the ice above them can quietly betray their presence. Jupiter is about 5 times farther from the sun than Earth is, and the sunlight there is thin and pale. Temperatures on those exposed surfaces fall far below the freezing point of water. If you judged only by distance and light, you would expect a solid, ancient crust and nothing more. But space exploration is an education in not trusting first impressions. In the late 1970s, Voyager 1 and Voyager 2 swept past Jupiter and sent back images that felt like postcards from a different physics. Europa appeared bright and smooth, crossed by dark lines, and marked by surprisingly few impact craters. A surface with few craters is, in planetary science, a kind of clock face. Fewer craters usually mean the surface is young, resurfaced or erased by some process. On Europa, that hinted at motion, ice shifting, cracking, perhaps even renewing itself from below. an active world where frozen did not mean still. Some regions on Europa looked like jumbled plates of ice, tilted and reassembled like broken sea ice after a storm. Scientists later called parts of this landscape chaos terrain, and they debated what it meant. One possibility was that warmer, softer ice rose from beneath, disrupting the crust like bread dough lifting a skin. The spacecraft's cabin stays dim, and you let the thought rest in your mind the way a pebble rests in a palm. A hidden ocean does not have to be proved by a single photograph, it can be inferred from several quiet lines of evidence that all point the same way. Over time, the picture gains weight. One of those lines of evidence comes from magnetism, a force you never see but can measure with patient instruments. Jupiter has a powerful magnetic field that sweeps around the planet and changes direction as it rotates. If a moon contains a conductive layer, like a salty ocean, that shifting field can induce an additional magnetic signal. Years after Voyager, the Galileo spacecraft arrived at Jupiter in the year 1995 and began repeated flybys of the large moons. Galileo carried a magnetometer and listened for subtle changes as it passed Europa, Ganymede, and Callisto. For Europa and Callisto, the data were consistent with induced magnetic fields, as if an electrically conductive layer were present below the surface. A salty ocean is not the only way to make a conductive layer, and scientists are careful about that. But on a moon made largely of water ice, with surface geology that suggests cracking and motion, a buried sea becomes a strong candidate. It is a hypothesis that fits several facts at once, which is how many discoveries begin. When you think of salt in an ocean, you might taste it on your tongue, but here it is chemistry and geology talking quietly to each other. If liquid water touches rock, it can dissolve minerals and carry ions that conduct electricity. That suggestion is important not because it proves life, but because it hints at interaction between water and stone. In your window, the stars drift so slowly that time feels wide. It is easy to forget that these hidden oceans are not all the same kind of place. Some may be thin layers, trapped between ice phases, while others may be deep global seas wrapped around a rocky core, changing with pressure and temperature. Ganymede, the largest moon in the solar system, is a reminder of scale. Scientists estimate that it contains more water, in ice and liquid combined, than Earth's surface oceans do. Much of that water may be locked in high-pressure ice, but models allow for a liquid layer as well, sandwiched where conditions permit. Farther from Jupiter, Callisto looks heavily cratered and ancient, a surface that keeps its scars. Yet even there, Galileo's magnetic readings hinted that something conductive could exist below, perhaps an ocean mixed with salts or ammonia. The evidence is more ambiguous, and that ambiguity is part of the story. Not every world speaks clearly. As your craft carries you outward in imagination, the conversation shifts from Jupiter to Saturn, where distance and cold deepen. Saturn's moon Enceladus is small enough to fit inside some United States states, and for a long time it seemed like it should be quiet. Then the Cassini spacecraft arrived in the year 2004 and found that the moon did not agree with expectations. Cassini watched Enceladus and saw plumes, jets of water vapor, ice grains, and other materials, spraying from fractures near the South Pole. Those fractures were later nicknamed tiger stripes because of their dark, linear appearance against bright ice. A plume is not a photograph of an ocean, but it is a direct sample of something warm and mobile under the crust. Cassini did more than take pictures. By tracking tiny changes in the spacecraft's speed during flybys, scientists measured Enceladus's gravity field, and found patterns consistent with the subsurface ocean beneath the South Polar region. They also detected salts and organic compounds in plume particles, suggesting that liquid water had interacted with rocky material. Titan, another moon of Saturn, complicates the picture further, in a gentle way. Its surface holds rivers and lakes, but those are made of liquid methane and ethane, not water, because the surface is so cold. Yet beneath Titan's thick atmosphere and icy crust, multiple lines of evidence suggest a water ocean may exist, hidden under layers you cannot see. When scientists talk about hidden oceans, they listen for several kinds of clues. They study surface geology for fractures and ridges that imply motion. They measure gravity to infer internal layers. They use magnetometers to detect conductive regions. They examine the chemistry of plumes and the way a moon's rotation wobbles, looking for the softness of liquid beneath ice. All of this is done with tools that feel almost delicate: radio signals, spectra, tiny shifts in trajectory. A spacecraft sends a tone back to Earth, and as it passes a moon, gravity changes that tone by an amount that can be measured. From that quiet change, layered interiors are inferred, as if you could hear the shape of a world. Light carries its own messages too, spread into color like a thin rainbow. Instruments called spectrometers divide reflected sunlight into bands and reveal the fingerprints of molecules on a surface. On Europa and other icy moons, these measurements show water ice, and in places they hint at salts, sulfur compounds, or irradiated materials altered by charged particles. You do not need to hold every method in your mind. You can let them drift past like the instrument lights, steady and patient. The important point is that hidden oceans are not a single claim, they are a growing map of evidence, gathered over decades by missions built to measure what eyes cannot. In the quiet of the cabin, a deeper question appears, soft-edged and unforced. If there is liquid water beneath ice, what else might be there? On Earth, where water meets rock and energy is present, chemistry becomes busy. But possibility is not certainty, and science is careful with that distinction. The search for life does not begin with declarations, it begins with conditions. Water is one requirement, and energy is another, and the right kinds of chemical building blocks matter too. Hidden oceans offer water by the scale of worlds, and they may offer energy through tidal heating or reactions between rock and water, but whether that becomes biology is still unknown. It helps to remember that darkness is not the same as emptiness. In the year 1977, scientists exploring Earth's deep ocean found hydrothermal vents where hot, mineral-rich water rises from the seafloor. Around those vents, ecosystems thrive without sunlight, powered by chemical energy, a discovery that widened the definition of habitable. That earthly lesson does not prove anything about Europa or Enceladus, but it changes what you are allowed to imagine responsibly. Life can, in some cases, live on chemistry rather than light. So when a distant moon offers liquid water, minerals, and energy, the question shifts from, could anything live there, to, what would need to be measured to know? Even the word, ocean, needs gentleness here. These seas may be trapped under ice so thick that no wave ever touches air. Their water may be mixed with salts or ammonia, their pressures far beyond anything at Earth's surface. They may be layered, with multiple kinds of ice above and below, like pages in a closed book. As you drift, you can feel the early mystery in its simplest form. Worlds that should be frozen may be warmed by tides, and worlds that look ancient may hide motion beneath their crusts. The solar system, once sketched as a set of dead spheres, keeps offering places where heat persists quietly, tucked away from sunlight. One of the most elegant pieces of that puzzle is orbital rhythm. Around Jupiter, Io, Europa, and Ganymede move in a repeating gravitational pattern called a resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4, a steady beat that helps keep their orbits slightly stretched instead of perfectly circular. That small stretch is enough. It keeps tidal heating working like a slow, persistent massage, especially for Io and Europa. Io becomes the most volcanically active body in the solar system, and Europa is kept warm enough that a global ocean remains plausible beneath its ice. The resonance is invisible, but its consequences are written across surfaces. Your ship does not need to hurry, and neither do you. In the parts ahead, You will glide closer to Europa's fractured plains, pass through the mist of Enceladus's plumes, and listen to Titan's muffled winds through the data of distant instruments. You will watch how each line of evidence, taken carefully, becomes a kind of shoreline. For now, you can rest with the basics. Ice can insulate, gravity can heat, chemistry can shift freezing points, and spacecraft can measure what the eye cannot. You do not need to remember every detail. You only need to let the idea settle. Like gentle snowfall, oceans can hide, and still be oceans. The cabin remains dim and steady, the starfield slow and untroubled. Somewhere ahead, beyond the reach of your window, worlds turn in silence, carrying their buried water through the long night. You stay with the hum of the ship, and with the thought of water still moving, patiently, under ice. Jupiter is still far ahead, but it already stops being a destination and becomes a force. Even through layers of shielding and silence, your instruments register the truth first, a deep, steady pull, as if space itself is leaning towards something immense. You did not come for oceans that glitter. You came for the ones that never meet a sky, sealed under ice so thick it can pretend nothing is happening. Hidden seas, kept alive by heat you cannot see, revealed only by the faintest hints a moon can't help but leave behind. In the cabin, the lights stay low and practical. The hum stays even. It feels less like a cockpit and more like a quiet screening room where the solar system is about to show you a scene it kept secret for centuries. For a long time, the outer solar system was assumed to be a deep freeze with a hard ending. Far from the sun, moons should be old, rigid, and finished. They should wear their craters like permanent scars and never bother to heal. Then the story snapped into motion, not with a grand announcement, but with photographs arriving like breath on cold glass. In the late 1970s, the Voyager spacecraft swept past Jupiter, and the moons stopped being points of light and became worlds with faces. The first face that changed everything was not Europa's. It was Io's. A moon that should have been quiet showed active volcanoes, plumes rising above the horizon, heat leaking into space as if the interior had never agreed to cool down. You can almost feel the moment it lands in the mind of any careful scientist. If Io is erupting now, then something is powering it now. Not leftover warmth. Not sunlight. Something continuous, something mechanical. That something is gravity, working like an engine you cannot turn off. Jupiter pulls. Io moves through the pull on an orbit that is not perfectly circular. The tug strengthens, then eases, then strengthens again, flexing the moon until rock behaves like it is being kneaded. Once you understand that a giant planet can warm a moon from the inside, Europa looks different even before you zoom in. It stops being cold. It becomes pressurized. It becomes stressed. It becomes a suspect with motive. Voyager's images of Europa arrive with a quieter kind of shock. The moon is bright, almost clean, with a surface that seems too young for its age. In planetary science, craters are a calendar. Europa's calendar looks partly erased. And then the lines appear, long, dark fractures stretching across the ice for hundreds, sometimes thousands, of kilometers. They intersect and curve and branch, like a record of a shell that has been pulled, twisted, and repaired over and over. The lines do not feel decorative. They feel like evidence. Like the moon is trying to hold itself together while something beneath keeps insisting on movement, you let the idea stay balanced on its edge. Ice cracks when it is stressed. Ice shifts when it floats over something softer. And if a shell of ice is shifting on a global scale, it starts to imply a layer beneath that is not fully solid rock. Your ship continues its quiet approach, and the story changes from a glimpse to an investigation. Voyager was a flyby, a quick look through a doorway. To learn what lives behind the door, you need repeated visits, measured from multiple angles. That is why the next chapter matters so much. In the year 1995, the Galileo spacecraft arrived at Jupiter and began looping through the system again and again, passing the moons like a careful detective returning to the same street lamp at different hours. Galileo carried a small complication that made the suspense sharper. Its high-gain antenna never fully opened, which meant the data had to trickle home slowly. Not a flood of answers, more like a drip, a drip, a drip, each packet precious. Even with that slow return, Europa's surface refused to simplify. Up close, the fractures were not just cracks. Many were ridges, paired ridges, raised seams where something had split the ice and then stiffened again, as if a wound had been stitched shut in freezing air. In places, broad bands cut across older terrain, looking like the surface had pulled apart and new material had risen to fill the gap. The ice did not look like a static crust. It looked like a skin under stress, able to open, to shift, to seal. Then there were the regions that earned their unsettling name, chaos terrain. Blocks of ice appear broken, rotated, and reassembled like rafts after a slow collision, frozen mid-motion. It doesn't look like impact damage. It looks like disruption from below. You keep your excitement quiet, because this is where discipline matters. Chaos can form in more than one way. Warm ice can rise without a full ocean reaching the surface. Melt pockets can soften a region without opening a window all the way down. The surface is speaking, but it can speak in riddles. So you do what explorers always do when images raise questions. You stop relying on eyes alone, and you start listening for the invisible. Galileo carried a magnetometer, an instrument that senses small changes in magnetic fields like fingertips reading Braille. It matters at Jupiter because the planet's magnetic field is powerful and restless, sweeping through space as Jupiter rotates. A changing magnetic field can provoke a response in a conductor. It is an old piece of physics, calm and dependable. If Europa hides a layer that conducts electricity, Jupiter's shifting field can induce electric currents there, and those currents create a secondary magnetic signal. During flybys, Europa answers back in that language. Galileo measures magnetic variations consistent with induction, as if something below the ice is conducting. The instrument does not shout the word ocean. It simply refuses to let the possibility go away. On a moon made largely of water ice, the simplest, strongest candidate for a conductor is liquid water mixed with salts. Salt water carries charged particles that can move, respond, and generate the kind of induced signature Galileo detects. You can feel the story tighten, because the clues are no longer isolated. A young, fractured surface. Ridges and bands that imply resurfacing. Magnetic behavior consistent with a conductive layer. Each one alone invites debate. Together, they start to sound like a chorus. And Galileo offers another kind of clue, one even quieter than magnetism, gravity. As the spacecraft passes Europa, Europa tugs on it, changing its speed by a tiny amount. Engineers track Galileo's radio signal and measure those tiny shifts with extreme care. From those variations, scientists infer how mass is arranged inside the moon. A layered interior leaves a different signature than a solid, uniform body. This is how you feel an ocean without seeing it, by weighing the moon and listening for hollowness where liquid would be. There is an elegance to it that fits the hush of your cabin. No drilling. No breaking the surface. Just physics, applied patiently, turning small changes in motion into a portrait of an interior. Light adds its own careful testimony. Spectrometers study reflected sunlight, splitting it into patterns that reveal what molecules dominate the surface. Europa's bright face is mostly water ice, but it is not pure. Darker materials stain and streak the crust. Those darker compounds are still argued over in detail. Some may involve salts that could have come from below. Some may be produced when radiation alters the surface, breaking molecules apart and recombining them into something new. Europa may be both a window and a mask. Because Europa lives inside Jupiter's radiation environment, its surface is constantly processed by charged particles. Over time, that processing can create oxidants, high-energy chemical compounds, stored in the ice like potential energy. This is where the tension becomes quietly electric. An ocean provides water. Rock below can provide minerals. Radiation above can help create reactive chemistry. If, and only if, material can move between surface and sea, then Europa becomes more than a sealed reservoir. It becomes a system. You look again at the cracks and bands with that question in mind. Are they only scars, or are they routes? Do they ever open deeply enough, even briefly, to pass chemistry downward or bring ocean material up? Somewhere behind all of it is the rhythm that keeps the engine running. Io, Europa, and Ganymede are locked in an orbital resonance that maintains a slight stretch in Europa's orbit. The pattern is steady. For every one orbit Ganymede completes, Europa completes 2, and Io completes 4. That ratio is not trivia. It is maintenance. It keeps Europa from settling into a perfect circle, and that small imperfection keeps the tidal flexing alive, orbit after orbit, century after century, long enough for water to resist freezing solid. The Jupiter system does not let you stop at one moon. Ganymede, enormous and complex, carries its own intrinsic magnetic field, a rare trait that tells you its interior is active in ways a frozen rock cannot be. It hints at layers, convection, and deep structure. Models for Ganymede allow a different kind of hidden water, liquid layers potentially sandwiched between forms of high-pressure ice, water behaving in unfamiliar phases under immense weight. Even the word ocean becomes textured here, more layered than you expected. Callisto looks like a world that kept every bruise, cratered and ancient, the opposite of Europa's youthful face. Yet magnetic measurements have been interpreted as compatible with induction there too, suggesting that even a moon that looks finished can hide something conductive beneath. And that is the broader turn Jupiter forces you to take. Hidden oceans may not be rare exceptions. They may be common outcomes of gravity, insulation, and time. The outer solar system may be full of water that learned how to survive without sunlight. You feel the mismatch again, and it never stops being thrilling. A tiny needle twitch in a magnetometer can imply a planet-wide sea. A slight Doppler shift in a radio signal can hint at layers of liquid miles beneath ice you cannot touch. Still, you keep one hand on the railing of uncertainty. Induction can suggest, not photograph. Chaos terrain can imply warmth without promising open water at the surface. An ice shell can be thin in places or thick enough to lock an ocean away. The story remains compelling because it remains testable. Science does not deliver its conclusions in a single dramatic shot. It builds them the way your ship crosses distance, steadily, repeatedly, with small corrections. Flyby after flyby. Measurement after measurement. The picture sharpens, not by luck, but by persistence. In the cabin's soft hum, you let Europa take shape as more than a name on a screen. A bright shell, cracked and stressed, floating over darkness. A world whose surface keeps rewriting itself, as if something below refuses to be silenced. You do not have to remember every mission detail to feel the pull of it. You only have to follow the thread. Fire on Io proves the engine, fractures on Europa hint at motion, magnetism suggests conductivity, gravity constrains the interior, chemistry raises the question of exchange. And now the journey naturally leans forward, toward the next kind of evidence, evidence so direct it almost feels unfair. Because beyond Jupiter, around Saturn, there is a small moon that does not merely hint at an ocean. It throws pieces of one into space. The ship stays quiet as the thought settles. You keep your breathing slow. And somewhere ahead in the dark, waiting patiently, is a plume you can fly through, mist from a hidden sea, drifting like a whispered invitation. Jupiter recedes until it is only a bright bead pinned to velvet, and you feel the mood change without any drama. The system that taught you to read cracks and magnetic whispers grows quiet in your window, and the lesson it left you is simple: cold worlds can stay active, as long as gravity keeps working. Your ship holds the same soft hum, the same restrained lights, while the next destination gathers itself from darkness. Saturn does not rush into view. It arrives like a slow reveal, a warmer-colored planet with rings that look, at first, like a thin breath of chalk across space. You are not coming here for the rings, not really. You are coming for the moment the hidden ocean story stops being an inference and becomes an encounter, water from a buried sea meeting a spacecraft in open space. You came because one moon here turns the idea of a hidden ocean into something the instruments can physically taste. Enceladus appears almost too small for that kind of role. It looks like a bright, clean bead of ice, the sort of moon you would expect to be finished, locked, and silent. If you only judged by size, you would never pick it as the place where an ocean reaches out first. But size is not the main variable out here. Heat is. Stress is. And the way a moon is squeezed by a planet can matter more than the diameter you read on a chart. Even Enceladus's orbit is kept slightly stretched by gravitational rhythm with neighboring moons, helping tidal flexing persist instead of fading away. Cassini arrived at Saturn in the mid-2000s and settled into a patient rhythm: loop, observe, loop again. It mapped moons and rings with the quiet stubbornness of a machine that does not get bored, and it kept returning to anything that behaved as if it had energy to spend. Enceladus kept offering that hint. Saturn's E-ring, a broad, diffuse band of icy particles, seemed brightest near the moon's orbit, as though something local was feeding it with fresh ice. The implication felt almost audacious: a small moon actively supplying a planetary ring. Cassini's cameras and particle instruments followed the trail. The closer the spacecraft looked, the harder it became to pretend the ring was just old debris. The particles were too clean, too reflective, too new. Somewhere, something was spraying them out. Then Cassini turned an infrared eye toward Enceladus's south pole and found warmth where cold should have dominated. Not a gentle, global thaw, but localized heat leaking through the crust, concentrated along deep fractures in the ice, long, parallel cuts that ran across the polar terrain like seams that refused to close. Those fractures earned their nickname the way nicknames usually happen in science: a little informal, a little astonished, instantly memorable. Tiger stripes. Dark lines on bright ice, and brighter heat along the lines than anyone expected. The phrase sticks because the pattern is unmistakable, the kind of mark you recognize even in a quick glance. When the plume came into view, it did not look like a single fountain. It looked like a breath held under pressure and finally released. Jets of water vapor and ice grains rose from the tiger stripes and spread into space, lit from behind, delicate and unmistakable against the black. You can sense the next question before it's spoken. Are the jets steady, or do they pulse with tides? Over time, Cassini saw the activity change with Enceladus's orbital position, as if the fractures opened and narrowed as the moon was squeezed, letting more vapor escape at some times and less at others. In your mind, the scene plays with a strange intimacy. Enceladus is venting. A world is leaking. A hidden reservoir is not merely suggested by graphs, it is physically present as drifting particles, thin enough to fly through, real enough to measure. Cassini did fly through. Each crossing was a sampling run, a spacecraft threading a mist that began, moments earlier, as liquid water or warm brine beneath the ice. One instrument drank the gas and sorted molecules by mass. Another caught dust grains like microscopic snowballs and read their chemistry from the way they struck and fragmented. The plume's main ingredient was water vapor, but the details mattered. Additional molecules appeared in the mix, including carbon-bearing compounds. You can imagine the data arriving as clean peaks on a display, each one a fingerprint, simple, undeniable, and still cautious about interpretation. Some of the icy grains carried salts. That one fact changes the interpretation of everything around it. Salts are easiest to explain if liquid water has been in contact with rock, dissolving minerals and carrying ions upward. It suggests an ocean that is not isolated from the interior, but chemically engaged with it. The grains were not all the same. Some looked like nearly pure ice, as if they condensed from vapor. Others looked more like frozen spray, rich in dissolved material, hinting at droplets flung up from a liquid reservoir and then instantly crystallized in near vacuum. Cassini's measurements did not stay in the realm of composition. They moved into structure. During close flybys, the spacecraft's radio signal shifted slightly as Enceladus tugged on it, and those tiny changes in speed let scientists map the moon's gravity field with extraordinary sensitivity. Gravity became a way of seeing through ice. A uniform, fully frozen interior would pull differently than a layered one. The pattern Cassini inferred fit a world with an interior that could rearrange mass, consistent with liquid water beneath the south polar region. Heat supported the same story from another angle. The South Pole was radiating more energy than sunlight could provide, concentrated along the tiger stripes, as if the fractures were both vents and radiator fins. Something inside was paying the energy bill, and paying it continuously. Even the way Enceladus rocked in its orbit mattered. A rigid shell locked to a solid interior would resist certain motions. Enceladus's subtle libration, the tiny back-and-forth wobble, fit better with a shell that can slip over something softer, like ice floating over liquid water. By now the narrative is almost too clean: plumes, heat, gravity, motion, all pointing toward an ocean. And still, science keeps one hand on caution. You consider alternatives, localized melt pockets, transient reservoirs, until the pile of evidence makes them harder and harder to hold. Then chemistry adds a new edge. In later analyses of plume data, scientists reported molecular hydrogen in the gas, a potential energy source that can be produced when warm water reacts with certain rocks. On Earth, similar reactions can supply fuel for microbial life near hydrothermal vents, independent of sunlight. Another set of whispers came from tiny grains in Saturn's ring environment, including very small silica particles interpreted as the product of hot water interacting with rock and then cooling quickly. It is the kind of evidence that points to activity at the seafloor, not just near the roof. You do not let that become a leap to biology. You let it become what it is, a sign that the ocean could be in contact with warm rock, and that energy could be flowing through the system in a form chemistry can use, persistent, renewable, and real for a very long time. Put the ingredients together and the scene becomes hard to forget. Liquid water sustained over time. Salts and organics carried upward. Possible chemical energy sources produced below. A pathway, fractures, to move material between interior and space. Habitability, not declared, but assembled. And Enceladus does something rare: it makes that assembly accessible. You do not need to drill. You do not need to melt through miles of ice. A spacecraft can sample an ocean by flying through a plume the moon itself provides, like an invitation that keeps repeating. In the quiet of your cabin, you also feel the weight of what that implies. If you can sample an ocean world, then exploration becomes a matter of care. It raises questions about cleanliness, about how to learn without contaminating, about touching lightly even when the evidence is close enough to taste. Saturn offers a second ocean world, but with a different curtain drawn across it. Titan does not vent water into space. Titan hides it behind a thick atmosphere and a surface shaped by liquids that are not water at all. It is a different kind of secrecy, and it makes you lean closer instead of moving on. At first, Titan looks almost gentle, an amber globe softened by haze, refusing to show you its surface in ordinary light. The atmosphere is dense, layered, and chemically rich, turning sunlight into a diffuse glow that makes the moon feel half-imagined. Cassini watched Titan for years and finally sent a probe, Huygens, down through the haze. The descent was slow, a long fall through orange clouds, and then a landing on terrain that looked strangely familiar, rounded ice pebbles, channels, plains that suggested erosion and flow. The familiarity is a trick. The temperature is too low for liquid water to shape those channels today. On Titan, the active surface liquids are methane and ethane, and they behave like a colder echo of Earth's water cycle, evaporating, condensing, raining, carving, pooling. Cassini's radar pierced the haze and mapped lakes and seas of hydrocarbons, especially near Titan's poles. Shorelines appeared and shifted. Dark basins filled. You can imagine rain falling in the dim light, not water on skin, but methane on cold ice, quietly building rivers in slow motion. And beneath all of that surface weather, Titan keeps an older ocean story hidden. Titan is large enough to retain heat for a long time, and its thick atmosphere and icy shell insulated. Models and measurements suggest a layered interior where a subsurface ocean of water, likely mixed with salts or ammonia, can persist beneath the crust. The clues for Titan are subtle. They come from gravity flybys, from the way the moon's shape bulges under Saturn's pull, and from how its outer shell seems to respond as if it is not welded to solid rock all the way down. A decoupled shell is easier to understand if there is liquid beneath it. Some interpretations also consider magnetic induction as Titan moves through Saturn's changing magnetic environment. A conductive layer could respond, leaving hints in the field measurements. Titan's ocean, if it exists, is a quiet one, more inferred than sampled, more hidden than Enceladus's sea. You let the contrast settle. Enceladus is small and sharp, with fractures that vent space and let you taste the sea. Titan is large and muffled, turning chemistry in its sky while guarding water below. Two ways to hide a sea, two ways for science to catch its shadow. Together, they widen the meaning of ocean world. One is a near-direct laboratory for subsurface water and seafloor energy. The other is a planet-like moon where surface chemistry and hidden water may run in parallel for ages, each influencing the other in ways still being measured. By the time you look back at Saturn's rings, the rings feel like more than decoration. They are part of the exchange, particles likely fed by Enceladus, shaped by gravity, sunlight, and collisions, a visible reminder that moons and planets do not simply orbit in isolation. The arc of your journey shifts again here. At Jupiter, you learn to infer oceans from scars and magnetic replies. At Saturn, you learn that sometimes the ocean finds a way to speak louder, sending out salt and organics as ice grains in a plume into the dark. In the cabin, the hum stays steady, and you keep your breathing slow. You do not need to memorize every instrument name or every molecule Cassini detected. What matters is the change in pressure behind the story. Hidden oceans are no longer rare guesses, they are places with signatures, heat that should not be there, gravity that feels layered, chemistry that tastes like brine. Saturn's light holds in your window like a lantern turned low, and you carry two impressions with equal clarity, a moon that exhales water into the dark, and a moon that breathes methane weather under a haze while guarding water below. You keep them close, letting their differences sharpen the same central truth. Beyond Saturn, other dim points wait, and some of them may hide seas of their own. But the lesson you take forward is already strong enough to shape the rest of the voyage. An ocean can stay hidden, and still reach out, if the physics is right and the cracks line up. And when it does, a spacecraft does not have to look away. It can pass through the mist, count what hits its instruments, and bring the taste of an alien sea home as data, one quiet particle at a time. In that soft contact, the solar system briefly feels less distant, and more like a place you can learn, carefully, by touch. Saturn slips behind you until the rings are only a thin scratch of light, and then not even that, just darkness where you remember them. The cabin stays steady and dim, and the ship's quiet systems keep time for you while the solar system spreads out like a deep, slow breath. Beyond Saturn, the ocean worlds do not stop. They simply grow harder to hear. The clues thin out, the distances stretch, and you begin to rely on older footprints, brief flybys, partial maps, single chances to look before a spacecraft vanishes into the next leg of its voyage. Your ship carries you into a region where sunlight feels diluted, more suggestion than warmth. It is a place where ice can keep its grip for ages, and where a buried sea, if it exists, can stay hidden simply because no one has returned often enough to ask the same question twice. So you reach for a different kind of character in the story, Voyager 2. A scout from another era, built to endure, crossing from giant planet to giant planet on momentum and careful navigation, bringing back scenes that are still, for many worlds, the only close-up pages we have. Voyager 2 arrived at Uranus in the year 1986, and Uranus refused to look normal. The planet rolls through space nearly on its side, making its seasons strange, and its magnetic field is oddly tilted and offset, as if the source inside is not neatly centered. The moons that circle Uranus came into view like pale coins, and then the images sharpened into surfaces with histories. Ariel showed long canyons and ridges, terrain that looks stretched and faulted, as if the crust had once been pulled apart from within and then left to cool. Umbriel looked darker and more heavily cratered, a face that holds onto old scars. Titania and Oberon appeared larger and steadier, with deep fractures and impact basins that hint at a past where the interior had enough heat to deform the shell. The details are faint, but they suggest something inside once warmed the ice from below, long enough to reshape it. Miranda, small and startling, looked like a world assembled from mismatched panels, cliffs and ridges stitched beside smoother plains. It feels like a visual shorthand for chaos in formation, a reminder that small bodies can experience episodes of internal activity and then fall silent again. Here, your ocean question becomes more careful. Voyager 2 did not linger. It did not orbit Uranus or perform years of repeated passes the way Galileo did at Jupiter or Cassini did at Saturn. It offered a glimpse, and then Uranus closed the door behind it. That matters because the strongest ocean evidence is often rhythmic. Induced magnetism is clearest when you pass a moon many times through a changing magnetic field. Gravity mapping improves when you can sample many trajectories. The subtle wobble of a floating ice shell stands out best when you can watch the motion build and repeat. So when scientists talk about possible oceans inside Uranus's larger moons, they do it in conditional language. Those moons are large enough to keep heat for a long time, and models allow that a buried ocean could persist beneath ice if the right ingredients are present. Everything depends on details a flyby cannot fully resolve. How much rock is inside, generating heat through slow radioactive decay? Whether antifreezes like ammonia are mixed into the water? Whether past tidal heating ever warmed the interior enough to start an ocean, and whether that ocean could survive as the system calmed. In the hush of the cabin, you let that uncertainty be part of the atmosphere rather than a flaw. A whispered ocean is still worth listening for. It is a reason to return with new instruments, to fly repeated paths, to measure magnetism and gravity with the patience the question demands. From Uranus, the story moves farther outward, toward Neptune, where the light is thinner and the distances feel almost ceremonial. Voyager 2 arrived in the year 1989, and the encounter it delivered has never really stopped echoing. It was, for decades, the farthest close look humanity would get at this system, a single pass preserved like a snapshot. Neptune appeared deep blue and windswept, but it was the moon that stole the scene. Triton slid into view as a bright world with a delicate atmosphere and terrain that looked young in places, as if the surface had been renewed after most of the solar system had settled down. Triton does not feel like it belongs to Neptune in a quiet, orderly way. Its orbit is retrograde, moving against the usual direction, a clue that it was likely captured, an immigrant from the Kuiper belt drawn in by Neptune's gravity and forced to adapt. Capture is violent in slow motion. If Triton's orbit changed dramatically as it settled, tides inside could have flexed it hard, turning orbital energy into heat. In that kind of history, ice can melt deep below, and an ocean can begin not as a gentle pond, but as an aftereffect of upheaval. Voyager 2 saw broad plains of frozen nitrogen and other ices, and then it saw something that felt almost unfair at that distance from the sun: active plumes. Jets rose from dark sources, and faint atmospheres carried their deposits downwind, leaving long streaks across the bright surface. The energy behind those plumes is still debated in detail. Sunlight can warm translucent nitrogen ice in a way that creates pressure beneath the surface, and internal heat may also play a role. What matters for you is the consistent theme: activity is a signpost, and Triton posted one. Even if some jets are powered close to the surface, Triton's overall youthfulness keeps the interior question alive. A world with a changing surface is often a world with energy still moving through it. And where heat persists inside ice, liquid water becomes a possibility you cannot ignore. Could Triton still carry a buried ocean today? It is plausible, and the plausibility matters because Triton would widen the ocean world family beyond classic moons like Europa and Enceladus. It suggests that even captured, distant bodies can join the pattern, given enough heat and enough time. As you drift onward, the solar system begins to feel less like separate chapters and more like a set of repeating mechanisms. Gravity flexes. Ice insulates. Salts and ammonia shift freezing points. Radioactive heat persists. Again and again, the same quiet physics offers water a way to remain liquid without needing sunlight. And then, beyond Neptune, you enter the realm of small, remote worlds where the sun looks more like a bright star than a furnace. This is where the ocean story becomes surprising again, because the bodies are smaller, and the cold is deeper, and your old assumptions try to return. Pluto is one of those worlds, long treated as a frozen relic at the edge of everything. And yet, when New Horizons arrived in the year 2015, Pluto refused to play the role of dead stone. It showed landscapes that looked young, structured, and strangely alive with slow motion. A bright plain of nitrogen ice sat like a calm, pale sea, with few craters, suggesting renewal. The surface looked as if it were being turned over from within, soft ice convecting slowly, carrying older material down and bringing fresher material up in a cycle too gentle to hear, but visible in the patterns it leaves. Nearby, mountains of water ice rose like bedrock, and fractures and troughs suggested that Pluto's outer shell had been stretched. Stretching is a kind of confession. It implies internal change, warming, freezing, shifting layers, something that altered the shape of the world until the crust had to crack. One way to stretch an icy shell is to have liquid beneath it. A subsurface ocean that cools and slowly freezes can change a body's volume and stress its crust. Instead of locking Pluto into perfect stillness, interior evolution can keep it tectonically expressive for long spans of time. Scientists are careful here, the way they should be. Pluto's ocean is not directly measured the way Enceladus's plume is sampled. It is inferred, from geology, from the youth of certain terrains, and from models of how a rocky interior could retain heat beneath a thick, insulating shell of ice. If Pluto does have an ocean, it likely relies on the same subtle helpers you have already met. Ice as insulation. Rock as a slow heater. Chemistry as a quiet adjustment, ammonia mixed into water, perhaps, acting like antifreeze and keeping a layer liquid longer in the deep cold. Charon, Pluto's large companion, adds its own story of internal change. Its surface shows immense canyons and signs that the interior once expanded or rearranged, consistent with a world that warmed, differentiated, and then cooled. Even a short-lived ocean, long gone, would still matter for what it reveals about heat and water. Here, you let uncertainty remain gentle. Some hidden oceans may be ancient and gone, frozen into layered ice. Some may persist today. The distinction matters, but so does the larger pattern. Water and heat have many ways to meet, even far from the sun. And the ocean story does not belong only to the outermost frontier. Closer in, between Mars and Jupiter, a different kind of hidden water narrative unfolded at Ceres. Spacecraft observations revealed bright salt deposits and evidence of brines, suggesting that liquid water once moved through its interior and, in places, may have lingered as pockets or reservoirs. It is not quite the same as a global ocean under an ice shell, but it rhymes with the theme: liquid sheltered from sunlight, chemistry recorded in salts, and a world that is more active than its distance and size might suggest. It softens the boundary between ice moons and rocky worlds. In the cabin's low light, this is where the big connection begins to take shape. You started with Europa's cracks and Enceladus's plume, expecting a handful of exotic exceptions. Instead, you keep finding variations on the same idea: oceans not at the surface, but held inside worlds like secret rooms. The solar system's hidden oceans are not all equally accessible. Some announce themselves with jets you can fly through. Some show only faint tectonic hints. Some may exist only in the past, their water now locked away as high-pressure ice or frozen layers that never again become liquid. But taken together, they suggest something quietly radical. On Earth, the ocean is a surface feature, open to sky. In the broader solar system, oceans may be mostly interior features, more abundant in volume, more common in location, and far more hidden from easy view. That changes how you think about habitability. It is no longer only a question of comfortable sunlight. It is a question of energy and chemistry, where water can stay liquid, where rock and water can meet, where gradients can persist, where time is generous enough for complexity to build. It also changes how you think about exploration. The easiest worlds to study are not always the most revealing. Enceladus offers samples but is small and dynamic. Europa offers volume and strong evidence but keeps its ocean sealed. Titan offers chemistry above and a possible sea below, wrapped in haze. Uranus and Neptune's moons sit like unopened letters on the far desk of the solar system, their pages barely glimpsed. Triton looks like a letter already torn open at the corner, showing motion inside. Pluto hints at an ocean through geology alone, a message written in slow ice. You feel, in the steady hum of life support, the patience required for the next steps. Ocean science at these distances is a slow art. It is built from careful trajectories, from years of cruise, from instruments that measure tiny changes in radio signals and faint shifts in magnetic fields, and still, the reward is intimate. A new kind of shoreline in the imagination. Water moving in darkness, not as a miracle, but as a consequence of physics repeating itself on different worlds, each time with a different accent. You can almost picture the hidden water as a slow pulse beneath frozen skin, keeping the idea of change alive. Outside the window, Saturn is gone. Uranus and Neptune are long behind their thin curtains of distance. Ahead is the realm of small lights and colder names, and your ship continues as it always does, quietly, steadily, letting the evidence arrive in its own measured way. You do not need to hold every candidate world in your mind at once. You can let them drift past like stars. The shape of the story is what you keep. Hidden oceans are not a single curiosity, but a class of places you can learn to recognize. Let the names fade if you want, keep the pattern. And as that realization settles, you notice the next question forming, calm and inevitable. If oceans can hide almost anywhere, how do you design tools to find them, and how do you choose which quiet sea to visit next? The journey is beginning to turn from finding oceans to deciding how to approach them. The farther you travel, the more the ocean worlds start to feel like a single, braided story. Not just where liquid hides, but what that liquid is doing, minute after minute, year after year, under ice that never opens to the sky. Your ship keeps its hush, as if it understands that the next question is quieter than the last. Finding a hidden ocean is one kind of thrill. Understanding whether it can stay chemically awake, whether it can support anything like a living system, is a deeper kind. You let the word habitability settle without letting it harden into a promise. Habitability does not mean life is there. It means the environment can, in principle, support life, given water, usable energy, and the right chemistry, held stable long enough for complexity to build. Water is the easiest part to say and the hardest part to truly picture. In the outer solar system, oceans are not blue surfaces under sun. They are pressurized interiors, wrapped around rock, capped by ice, sometimes layered in strange phases as depth and pressure change the rules. If sunlight cannot reach these seas, then life, if it exists, would need another power supply. On Earth, the obvious answer is the sun, but Earth has a quieter answer too, one discovered in the deep ocean. Chemistry can feed ecosystems. In the year 1977, scientists found hydrothermal vents on Earth's seafloor, places where hot, mineral-rich water rises from rock and meets cold ocean water in darkness. Around those vents, life thrives without photosynthesis, building food webs on chemical energy. You picture it the way your mind naturally does at night, a black plain of deep water, columns of mineral-laced water rising like smoke, and living things clustered around heat and chemistry like travelers around a lantern. The scene is real, and it changed what habitable could mean. It also changed how you look at a moon like Enceladus. A plume is not only an aesthetic spectacle. It is a clue that water is moving, that heat is leaking, and that chemistry from the interior can be carried upward in a form instruments can read. Cassini tasted that chemistry in the plume: water vapor, icy grains, salts, and carbon-bearing molecules. Those are not signatures of life on their own. They are signatures of an ocean that is not isolated, an ocean that has been in contact with rock and has carried minerals with it. Some analyses also reported molecular hydrogen in Enceladus's plume gas, a molecule that can be produced when liquid water reacts with certain rocks. On Earth, hydrogen can serve as chemical fuel for microbes in dark environments, not as proof, but as possibility. You keep the logic clean in your mind, the way you keep the ship's instruments calibrated. If hydrogen is being produced, then reactions may be happening at or near the seafloor. If reactions are happening, then energy gradients exist. And where gradients exist, chemistry has something to do. One of the key reactions scientists discuss is serpentinization, where water alters certain iron-rich rocks and releases hydrogen, often producing alkaline fluids. You can imagine seawater sinking into fractured rock, warming, reacting, and rising again changed, carrying energy in its new chemistry. The ocean itself becomes more than a volume of liquid. It becomes a circulation system, like blood in a body, moving heat and chemicals from one region to another, building differences in composition that can be harvested by any chemistry capable of using them. Europa offers a different kind of potential energy story. Unlike Enceladus, Europa sits inside Jupiter's intense radiation environment, where charged particles can split molecules on the surface and create oxidants, reactive chemical species stored in the ice like quiet batteries. If surface material can be carried downward, through cracking, melting, or slow recycling, those oxidants could meet, reducing chemicals from the interior. That meeting point matters. Life, as we know it, often lives at boundaries, where one chemical state presses against another. You picture those boundaries as invisible shorelines under ice. Not a beach, but an interface, ocean water meeting rock, or ocean water meeting modified surface materials. A place where reactions can run continuously, not once, not briefly, but over long spans of time. Time matters as much as energy. A short-lived lake under ice is interesting. A stable ocean that persists for millions of years is a different category of opportunity. Your ship's steady drift through space starts to feel like a metaphor for that requirement: slow, persistent, patient. The question of rock contact is central, and not all ocean worlds offer it equally. If high-pressure ice forms between a deep ocean and a rocky mantle, it can act like an extra wall, limiting exchange. In that scenario, the ocean can exist and still be chemically quieter. Ganymede is where that complexity becomes hard to ignore. Its size allows multiple layers: ice, liquid, and high-pressure ice arranged like stacked geology. An ocean there could be vast and still relatively separated from the rock that would enrich it. Titan complicates it in another direction. Its thick atmosphere allows complex organic chemistry to flourish above, while a water ocean, if present, hides far below. The surface can look alive with rivers and lakes of methane even while the water ocean remains sealed, slow, and distant from that upper chemistry. You hold these differences gently, because they are the heart of the mystery. The solar system may have many oceans, but not every ocean is equally fed. Some are stirred by tides. Some are warmed mainly by slow interior heat. Some are connected to rock. Some may be layered away from it. Even the ice shell is not just a lid. Its thickness and behavior decide what can move between surface and sea. A thin shell can crack more easily, allow brines to rise, and possibly allow oxidants to be delivered downward. A thick shell can preserve an ocean and still keep it isolated. Europa's surface hints at exchange, but it does not guarantee it. Chaos terrain may form from shallow melt pockets rather than direct openings to a global sea. Ridges may be places where warm ice rose and froze again, leaving scars that are compelling but still ambiguous. So your story becomes a story of measurements, not wishes. Ice-penetrating radar can search for internal structures that suggest water pockets or changes in ice properties with depth. Gravity measurements can constrain the thickness of layers. Magnetometers can listen for conductive responses consistent with salty oceans. Your ship's cabin stays dark enough that the instrument lights feel like constellations of their own. You imagine a radar pulse sinking into ice and returning with a delayed echo, like a call into a canyon. A different delay, a different texture in the return signal, and the interior becomes slightly less imaginary. Heat is another voice in this chorus. Infrared mapping can reveal warm regions that suggest active tectonics or shallow liquid reservoirs. On Enceladus, heat concentrates along tiger stripes. On Europa, subtle thermal anomalies could hint at regions where the shell is thinner or where warm ice is rising. Then there is rotation, a slow movement that reveals hidden softness. If a moon's ice shell is decoupled from its interior by a liquid layer, it can wobble slightly differently under tidal forces. That wobble is small, but it carries information, like a tremor that hints at what is underneath. Even with all these tools, the most interesting question remains stubbornly human: what would count as convincing evidence of life? Not a single molecule, not a single dramatic detection, but a pattern that resists non-biological explanation. Scientists talk about biosignatures in careful language, particular distributions of organic molecules, certain ratios of isotopes, chemical disequilibria that are hard to sustain without continuous processes. The emphasis is always on combinations, multiple lines of evidence pointing the same direction. You picture a single icy grain from Enceladus's plume drifting into a detector. It shatters, turns into a spectrum, becomes data. The grain does not carry a label that says alive or not alive. It carries only composition, and it is up to interpretation to stay disciplined. That discipline is why planetary protection matters, and you feel its weight in the hush. If an ocean world might be habitable, then it must be approached with care. A contaminated sample is worse than no sample, because it confuses the story and risks the place itself. Spacecraft are assembled in clean environments, baked and sterilized as much as engineering allows, not as ceremony, but as method. The goal is to learn without leaving a biological fingerprint that could outlive the mission and blur the meaning of future discoveries. As you drift through these thoughts, the ocean worlds begin to feel less like destinations and more like responsibilities. They are not blank stages waiting for a dramatic reveal. They are complex systems that have been running for geological time, doing chemistry under ice long before humans learned to ask questions. And still, the pull of the question is irresistible. If life can exist without sunlight in Earth's deep sea, then a hidden ocean warmed by tides and fed by rock becomes a plausible habitat. Not guaranteed. Not promised. Plausible in the strictest, most interesting sense. The big picture begins to sharpen. The classic, habitable zone, is not the only place for habitability. A planet can be too cold on its surface and still keep liquid water inside. A moon can be far from the sun and still have energy, gradients, and chemistry that never stop moving. That realization changes the scale of your imagination. Earth is not the only kind of water world. In terms of sheer volume, subsurface oceans may contain more liquid water than all the surface oceans combined, distributed across moons and dwarf planets that never sparkle blue in reflected sunlight. You let that idea sit with you as the ship's hum continues. Not to inflate hope, but to widen context. The solar system is not a simple map of alive near the sun, dead far away. It is a system where heat can be traded through gravity, where ice can insulate, and where liquid can hide and persist. Somewhere ahead, missions are being built around these questions. Flybys designed to map Europa's ice and chemistry with repeated passes. Long studies of Jupiter's moon system to understand magnetic environments and interior layering. A rotorcraft designed to explore Titan's organic landscapes from close range. Each mission is, in a way, a different kind of question written into hardware. Is the ice thin anywhere? How salty is the ocean? Does the ocean touch rock? Are there places where surface chemicals cycle downward? Do plumes carry interior material, and if so, what is in it? You do not need to know the answers to feel the story tightening. You only need to recognize that the search has matured. It has moved from wonder to strategy, from maybe there is water to here is how we will test the thickness, the chemistry, and the energy. In the window, the stars keep their slow drift, and you stay in your seat, calm and attentive. The hidden oceans are still hidden. But the questions you are asking now are sharper, and sharper questions have a way of turning darkness into something readable. You carry one final thought forward, like a quiet compass needle. If life exists in any of these sealed seas, it will not announce itself with fireworks. It will be subtle, persistent, chemical. And that means the story will not end with a single moment of discovery, but with patient evidence accumulating until the simplest explanation becomes the most extraordinary one. The ship stays steady as you let that possibility remain what it is, an open question with real stakes and real methods. Ahead, you will return from the big picture to specific worlds again, back to ice shells, plumes, and measuring techniques, with a new focus on the details that matter most: exchange, energy, and time. The ship's hum stays steady as your questions sharpen, because this is the point where wonder turns into a plan. You are no longer only asking whether hidden oceans exist. You are asking how to approach them without guessing, how to measure what is buried, and how to tell a chemical coincidence from a living pattern. Outside the window, the stars look indifferent, but inside the cabin the instruments feel like a set of senses you are learning to trust. A camera is sight, yes, but it is also a clock, because craters and fractures tell time. A magnetometer is hearing, tuned to whispers of salt water. A radar sounder is touch, pressing a pulse into ice and listening for what answers back. You let your attention rest on the idea that an ocean world is not a single destination. It is a layered system with doors you may never open, only outline. The art is to trace the edges so clearly that the unseen becomes hard to deny. First comes the surface, because the surface is where stress leaves handwriting. On Europa, the handwriting is long and relentless, ridges like seams, bands like healed wounds, chaos terrain like a page torn up and taped back together. High-resolution imaging does not just make prettier pictures. It tells you where the shell has been weak, and where it might still be thin. Then comes composition, because ice can lie by looking clean. Spectrometers split reflected light into subtle patterns, telling you where the surface is pure water ice and where it is stained with salts, sulfur compounds, or materials altered by radiation. Those stains matter because they hint at exchange, at chemistry that traveled from elsewhere. You imagine an orbital path that repeats, again and again, not for drama, but for confidence. One pass can be a fluke. Many passes become a map. Repetition is how you turn a strange patch of terrain into a story you can test. Radar is the tool that makes the hair on the back of your mind lift, even in this quiet cabin. A pulse goes down into ice and returns in echoes, delayed and softened, carrying information about layers, pockets, and boundaries. A strong return can suggest a change in material, and in the right context that change can point toward liquid water. But radar does not hand you an ocean like a clear photograph. It gives you a puzzle of reflections. You learn to read the puzzle the way you might read the faint sound of rain through a roof, knowing it tells you something real about what you cannot see. Gravity is subtler still, and somehow even more intimate. The spacecraft never touches the moon, yet the moon reaches up and tugs the craft's motion by tiny amounts. By tracking those changes in speed with exquisite care, you can infer how mass is arranged inside, where layers begin and end, and how thick a shell might be. Topography matters too, because oceans deform their worlds. An ice shell over liquid can rise and fall slightly under tidal forces. If you can measure the shape of the surface precisely, its bulges, its gentle breathing, you can infer where the shell is stiff and where it is letting something move beneath it. Magnetism returns as the strangest kind of confirmation. A changing magnetic field sweeping past a moon can induce currents in a conductive layer. If the layer is salty water, it answers with a secondary field, not loud, not dramatic, but stubbornly consistent. With enough flybys, that answer gains the weight of a signature. Thermal mapping adds another layer of tension, because heat is hard to hide. Warm regions can mark thinner ice, active fractures, or places where warmer ice is rising. On some worlds, heat is a signal flare. On others, it is a faint glow you only see by collecting patient, careful data. And when a world offers plumes, the whole relationship changes. Instead of inferring interior chemistry through a roof, you sample the interior as it arrives to you, grain by grain. You can measure salts, organics, and the distribution of molecules, and you can begin asking not only what is present, but how it was made. You keep your excitement disciplined here, because chemistry is generous. Many molecules that matter to life can be made without life. The question is not whether organics exist, but whether their patterns make sense as geology alone, or whether they point to something that is continually organizing itself against the drift toward equilibrium. You picture a plume particle hitting a detector, breaking apart into a spectrum, becoming a line of peaks and gaps. It is a small collision inside a quiet box, yet it carries hints from a seafloor no sunlight has ever reached. The scale mismatch never stops feeling unreal. Europa remains the most famous test of patience. The evidence for an ocean is strong, but the path to sampling it is not straightforward. You need to know whether any material from the ocean reaches the surface, and if it does, where it does so most recently, before radiation and time blur the chemistry. There have been tantalizing hints that Europa may sometimes vent material into space, but hints are not the same as a plume you can count on. That uncertainty becomes a story engine of its own, the hunt not for proof of water, but for the pathways water may use to communicate. Ganymede asks a different set of questions, because it carries its own magnetic environment. Its intrinsic field can complicate the induced signals you use to infer an ocean, like trying to hear a whisper inside a room with a steady fan running. The reward, if you can untangle it, is a world whose interior may be layered in ways that challenge your intuition. Callisto, cratered and ancient, sits like a reminder that silence at the surface does not guarantee stillness inside. If it holds a conductive layer, it may be a quieter ocean world, preserved rather than venting, stable rather than expressive. Worlds like that test the limits of your instruments and your patience. Enceladus, by contrast, feels almost unfairly cooperative. It gives you heat along its tiger stripes, a plume you can pass through, and chemistry that points toward water-rock interaction. It is the ocean world that turns theory into a route you can plan. Yet even there, the most important questions remain open. How thick is the ice above the ocean, region by region? How the plumbing works between seafloor and vents? Whether hydrothermal activity is steady or episodic. Whether the ocean is chemically uniform or stratified, with layers that keep certain reactions confined. Titan pulls your attention in a slower, stranger way. Its surface is busy with methane weather, dunes, rivers, and lakes, while its water ocean, if present, stays locked beneath. With Titan, you are studying two chemistries at once, organic chemistry in the atmosphere and on the surface, and water chemistry deep below. A mission that can move through Titan's air changes the kind of story you can tell. It allows you to visit multiple sites, to compare different terrains, to look for places where the icy crust may have brought water-related materials closer to the surface in the past. Titan is less about a single dramatic vent and more about a whole landscape of clues. As you consider all these worlds together, you notice the same questions repeating with different accents. Is the ocean in contact with rock? Are there chemical gradients that can do work? Is there a route for oxidants or organics to move between surface and sea? And, above all, how long has the system been stable? Time is the quiet requirement that holds everything together. Life, as far as we understand it, is not a flash. It is a long negotiation between chemistry and environment. A brief melt event may not be enough. A long-lived ocean, warmed gently and steadily, is a different class of possibility. You let your mind return to Earth's deep ocean vents, not as an analogy that proves life elsewhere, but as an existence proof that life can run on chemical disequilibrium. On Earth, microbes exploit boundaries, between alkaline vent fluids and acidic seawater, between reduced minerals and oxidized compounds. On an ocean world, those boundaries could exist too, if the plumbing and chemistry allow it. Europa's surface radiation may create oxidants that store energy in the ice. If those oxidants are transported downward, they could meet reduced chemicals from the interior. Enceladus may generate molecular hydrogen through water-rock reactions. In both cases, the theme is the same: energy is not a substance, it is a difference, and oceans can preserve differences. Your ship systems are calm, but the implications feel larger than the cabin. If habitable environments do not require sunlight, then the classic idea of the habitable zone becomes only one chapter of a longer book. Oceans can hide inside moons, dwarf planets, and worlds you would once have dismissed as frozen debris. That book has a careful tone, because it must. The challenge is to keep your narrative compelling without turning it reckless. You are not hunting for a headline. You are building a case that can survive skepticism. This is where the idea of landing starts to hover at the edge of your thoughts. An orbiter can map, listen, and infer. A lander can taste surface chemistry directly and measure the physical properties of ice where it stands. But landing on an ocean world is not like landing on a quiet plain. It is landing on a surface that may be cracked, jagged, or electrically charged by its environment. Jupiter's radiation adds another layer of difficulty, pressing time limits onto sensitive electronics and complicating long surface operations. You can feel how the environment itself becomes a character, antagonistic not out of malice, but out of sheer physics. Then there is the idea that returns again and again in late-night conversations about ocean worlds, going through the ice. A melt probe, a cryobot, a slow descent through a shell that may be miles thick. It is a concept that feels both inevitable and impossibly ambitious, like planning to lower a microphone through a mountain. Even if technology makes it possible, responsibility remains. Planetary protection is not an afterthought. If a world might be habitable, you cannot arrive carelessly. You cannot bring Earth's biology as a stowaway and then claim any discovery is clean. So exploration becomes a balance between curiosity and restraint. You design missions to learn as much as possible from above, to sample plumes when nature offers them, to land only when you can do so responsibly, and to interpret data with humility. You feel the story tightening toward its modern shape, a network of missions, instruments, and ideas that together make the hidden oceans less hidden. Not by prying them open, but by mapping their outlines until the interior becomes a confident inference, and then, in rare cases, a sample you can analyze. There is also a new kind of question now, one that sits beyond the first thrill of discovery. If the solar system has many ocean worlds, what does that mean for life as a cosmic phenomenon? Does it mean life is likely, because the ingredients are common? Or does it mean life is rare, because even common ingredients do not guarantee the right sequence of events? You do not answer that in a single breath. You let it remain open, because mystery is not a failure here. It is the reason the journey continues. I in the cabin, the steady hum does not change. Your body stays supported, your eyes half-lidded if you want them to be. The work of the story is being done in your imagination and in the instrument's quiet logic: measure, compare, repeat, constrain. Soon, you will return to the ocean worlds one by one again, not to reintroduce them, but to walk closer along their edges. To feel where the evidence is strongest, where it is weakest, and where a future mission could press gently and learn the most. For now, you keep one thought like a warm object in your palm. The most profound places in the solar system may be sealed and dark, with no sky above them at all. And yet, through cracks, fields, gravity, and drifting grains of ice, they still find ways to be known. The cabin is the same quiet room it has been all along, with dim panels and a steady hum that never asks anything from you. Outside the window, the stars keep their distance, and the solar system feels less like a map now and more like a long, gentle thought. You set out to find oceans with no shorelines. Not the kind that shine under sunlight, but the kind that stay sealed under ice, moving in darkness for ages, hidden so completely that only careful measurements can prove they are there at all. And slowly, world by world, you learn that the cold does not always win. You learn that ice can be a lid, and a lid can be protection. You learn that a small amount of heat, held close and renewed steadily, can keep liquid water from surrendering to frost. At Jupiter, the lesson began with a contradiction you could not ignore. Io burned with volcanoes, proving that gravity can make heat. Europa, bright and fractured, looked too young to be dead, as if its surface had been broken and repaired again and again. You remember the way evidence arrives out there, not as an announcement, but as a pattern. A smooth surface with few craters. Ridges that look like stitched seams. Chaos terrain that looks like ice rafts frozen mid-drift, hinting at something softer beneath. You remember how Galileo listened for what eyes can't see. Jupiter's changing magnetic field swept past Europa, and Europa answered back with a response consistent with a conductor below, one of the best clues you can have for a salty, buried ocean. You remember how gravity became a kind of touch. Tiny shifts in a radio signal, measured with patience, revealing that mass inside a moon is not arranged like a solid stone. Layers matter. Softness matters. A hidden sea changes the way a world holds itself together. Then Saturn arrived like a quieter lantern, and the ocean story found its most direct voice. Enceladus, small enough to underestimate, opened fractures near its south pole and let space taste what had been hidden under ice. Cassini flew through that mist, and the plume turned into data, water vapor, ice grains, salts, carbon-bearing molecules. A sea you could not see became a sea you could sample, one drifting particle at a time, as if the moon itself wanted to be understood. The heat along the tiger stripes joined the chemistry, and the gravity measurements joined the heat, and the wobble of the moon joined the gravity. Evidence stacked gently, until the simplest explanation became difficult to avoid: liquid water beneath, warmed and active, connected to processes deep inside. Titan offered a different kind of ocean world, wrapped in haze and patience. Its surface hosted rivers and lakes, but made of methane and ethane, not water. Beneath that alien weather, a quieter water ocean remained a strong possibility, inferred through the moon's structure and motion. Farther out, the story became fainter, but not less compelling. A single flyby can still leave fingerprints, a young-looking surface, unexpected activity, fractures that suggest a past warm enough to move ice like slow clay. Triton's plumes reminded you that distant worlds can still be restless. Pluto's young terrain and stretched crust suggested that even at the edge of the sun's reach, a buried ocean can remain plausible when insulation, chemistry, and interior heat cooperate. By the time you gathered these chapters together, the idea changed scale in your mind. Earth's ocean is a surface feature. In the wider solar system, oceans may be mostly interior features, more common in location, often larger in volume, and hidden beneath ice that never breaks into open horizon. And because these oceans are hidden, the way you know them is also different. You rely on echoes and tugs and whispers, radar returns, magnetic induction, gravity fields, thermal maps, and the quiet chemistry carried upward in cracks and plumes. That is why the question of habitability becomes a question of gradients. Water matters, but water alone is not a living system. What matters is energy that can be used, chemistry that can keep changing, and pathways that allow different materials to meet. On Earth, deep ocean life taught you that sunlight is not the only power source. Chemistry can do work. Boundaries can feed ecosystems. A seafloor can be alive with reactions that never see a sunrise, as long as heat and rock and water keep moving together. So when Enceladus offers salts and organics in its plume, you don't call it life. You call it contact, water that has touched rock, water that has carried minerals, water that suggests an interior still doing chemistry instead of simply freezing into silence. When Europa offers a processed surface inside Jupiter's radiation environment, you don't call it life either. You call it potential energy, oxidants that might be created at the surface, stored in ice, and possibly carried downward if the shell ever opens pathways deep enough. Still, the open questions remain, and they are part of the calm honesty of this story. How thick is the ice, really, in the places that matter most? How salty are these oceans? Do they touch rock directly, or are they separated by layers of high-pressure ice that quiet the chemistry? How often do fractures connect surface to sea? Are Europa's possible plumes real and repeatable, or rare and fleeting? Does Enceladus's seafloor host steady hydrothermal activity, or does it pulse in episodes that change the ocean's chemistry over time? And then there is the hardest question, asked with the most restraint. If there is life, how would you know without fooling yourself? Not with one molecule, not with one exciting plot point, but with patterns, ratios, isotopes, disequilibria, that stay consistent under repeated scrutiny. This is why modern exploration is built around patience. Missions are designed to return again and again, to map the same places in different ways, to layer measurements until the interior becomes readable without ever being seen directly. Europa is approached with cautious repetition, because Jupiter's radiation makes time expensive. You take what you can, pass by pass, radar for structure, spectroscopy for composition, magnetism for conductivity, gravity for layers, thermal imaging for hints of warmth. Ganymede is approached with a different rhythm, because its size and intrinsic magnetic field add complexity. Understanding its interior means untangling signals carefully, accepting that ocean there may mean multiple layers behaving in unfamiliar ways. Titan is approached like a slow, wide landscape, where you can move through the air and visit many places. The ocean stays buried, but the surface chemistry and geology can still tell you how materials move, where they concentrate, and where the crust might once have been warm enough to blur the boundary between surface and interior. Enceladus remains the rare gift, a world that offers samples without drilling. And even that gift comes with responsibility, because any place that might be habitable deserves careful handling, careful cleanliness, and careful interpretation. Planetary protection is the quiet promise beneath the science. Learn without leaving a biological fingerprint. Touch lightly. Keep the measurements honest. Do not carry Earth's life as a stowaway and then mistake your own shadow for discovery. In the end, the journey gives you something steady whether or not life is ever found. It gives you a new picture of the solar system as a place where heat can persist, where water can stay liquid in hiding, and where oceans can exist without sky. If life is found, it will change the way you understand your own world, not because it would be dramatic, but because it would mean biology is not a singular accident. It would mean the universe can build living systems more than once, given the right conditions and enough time. And if life is not found, the oceans still matter. They still teach you what water does under pressure and cold. They still show you how planets and moons exchange energy through gravity. They still expand what habitable can mean, even if the answer remains quiet. You don't need to hold every mission name in your memory. You don't need to keep every mechanism straight. You can let the details drift away like distant lights, because the shape of the story is what stays. There are oceans beneath ice. There is heat in places sunlight cannot reach. There are worlds that look still and yet remain active underneath, reshaping themselves slowly, patiently, in the dark. The ship continues to hum, faithful and soft. The instrument lights remain low, like a calm constellation inside the cabin. The stars outside drift at their unhurried pace, and nothing asks you to be alert in a hard way. If your mind wants to replay the journey, it can. Jupiter's fractured Europa. Saturn's venting Enceladus. Titan's haze and methane rain. Distant worlds that hinted at hidden water through youthfulness and cracks and motion. And if your mind does not want to replay it, that's fine too. You can simply keep the feeling of it, curiosity held gently, science treated with respect, the universe made a little wider without becoming loud. You are still here, in the quiet. The ship's sound is steady enough to blend with your breathing. The darkness beyond the window is calm, not empty, and it does not demand an ending more dramatic than rest. So you let the last thought settle like a small weight becoming warm in your palm. Somewhere, under ice, an ocean moves in darkness. It does not need an audience. It does not need you watching. It simply continues. And as you release the picture, you return your attention to something closer than any moon. The softness of your bed. The heaviness of your limbs. The slow, easy rise and fall of your breath. You don't have to remember any of this. You don't have to solve it. You can let the hidden oceans keep their quiet motion while you stay here, safe and still, letting sleep arrive the same way the stars drift past your window, slowly, gently, without effort.